Hello there, and welcome to a gentle exploration of something extraordinary. Tonight, we will journey inward, beneath the surface of skin, into the quiet rivers that flow through every living moment. We will discover the hidden world of blood, the crimson tide that carries life itself through endless pathways, working tirelessly while you rest, while you dream, while you simply exist. Blood is both ordinary and miraculous. It flows through you now, as it has since before your first breath, as it will until your last. It asks nothing of you, yet gives everything. Within its depths lie stories of survival, of adaptation, of connection to every ancestor who came before. If you enjoy these quiet explorations, I invite you to settle in deeply, to let your breathing slow, and to allow the calm rhythm of this journey to carry you wherever you need to go. Let's begin. The river, within every moment of your life. Blood moves through you in silence. Right now, as you read these words, or listen to this voice, approximately 5 liters of blood circulate through your body, traveling through vessels that, if laid end to end, would stretch more than 60,000 miles. That's enough to circle the Earth more than twice, yet this entire network fits within you, folded and coiled into every space, reaching every cell, touching every part of who you are. This river never stops. It flows through you when you sleep, when you wake, when you laugh, or cry, or sit in perfect stillness. Your heart beats about 100,000 times each day, and with each beat, blood surges forward, carrying oxygen, nutrients, warmth, and life itself to every corner of your being. It is the most constant companion you will ever have, more faithful than any friend, more reliable than any promise. Blood is ancient. The blood flowing through you now connects you to every human who ever lived, to ancestors who walked across continents, who survived ice ages and droughts, who passed down through generations the very chemistry of survival. In your veins flows the echo of that persistence, refined over millions of years into something both simple and profound. The color of life. Blood is red. This is one of the first things we learn as children, one of the most obvious truths about our bodies. Yet even this simple fact holds wonder. Blood is red because of iron, the same element that rusts metal and colors the soil of distant planets. Within each red blood cell, iron atoms sit cradled in molecules of hemoglobin, ready to bind with oxygen, ready to carry it wherever it's needed. When blood is rich with oxygen, freshly filled from the lungs, it glows bright scarlet, vivid and vital. This is arterial blood, flowing away from the heart, carrying energy to muscles, organs, and brain. When blood has delivered its oxygen and gathered carbon dioxide in return, it darkens to a deeper crimson, almost burgundy. This is venous blood, making its way back to the heart and lungs to be renewed. The redness of blood is life made visible. In ancient times, people understood blood's importance, even without knowing its mechanisms. They saw that blood loss meant weakness, that its presence meant vitality. They were right, though they could never have imagined the microscopic miracles occurring within each drop, the endless cycles of exchange happening billions of times each second, the quiet maintenance of existence itself. Some creatures have different colored blood. Horseshoe crabs have blue blood, copper-based instead of iron-based. Some marine worms have green or purple blood. But for humans, for mammals, for the warm-blooded creatures who walk and run and dream, red is the color of life, painted by iron, carried in rivers beneath the skin. The heart's endless song. At the center of this river sits your heart, a muscle about the size of your fist, beating steadily in the darkness of your chest. It has been beating since before you were born, starting its rhythm when you were still smaller than a grain of rice, when you existed only as potential. And it will continue, faithful and tireless, for as long as you live. The heart is divided into 4 chambers, 2 atria and 2 ventricles, working in perfect coordination. Blood flows in from the body, depleted of oxygen, into the right atrium, then down into the right ventricle. From there, it's pumped to the lungs, where it releases carbon dioxide and gathers fresh oxygen. Then it returns to the left atrium, flows into the left ventricle, and is sent surging out through the aorta to begin its journey through the body once more. This cycle happens about once every second at rest, faster when you move or feel excited, slower when you sleep deeply. The heart knows what you need without being told. It responds to hormones, to nerve signals, to the chemical messages floating in the blood itself. It is both a pump and a listener, both a commander and a servant. Ancient peoples believed the heart was the seat of emotion, the center of thought and feeling. They were not entirely wrong. The heart responds to emotion, speeding up with fear or joy, slowing with peace and contentment. Even today, we speak of heartache, of matters of the heart, of following our hearts. The metaphor persists because the connection feels true, felt in the chest during moments of intensity. Your heart began beating about 3 weeks after you were conceived. That first flutter of cells organizing into rhythm, that initial pulse, marked the beginning of a journey that continues now, in this moment, as you rest and listen. The same heart that beat in the womb beats now, grown larger, stronger, but still performing the same essential task, moving blood, moving life, never stopping, never failing, until the very end. Red blood cells, the carriers. If you could shrink down small enough to ride along in the bloodstream, you would find yourself surrounded by red blood cells, millions upon millions of them, all traveling together in a vidnik, crowded river. These cells are remarkable in their simplicity and their purpose. They have one job: to carry oxygen, and they do it with extraordinary efficiency. A single drop of blood contains about 5 million red blood cells. In your entire body, there are roughly 25 trillion of them, making them by far the most numerous cells you possess. They are shaped like biconcave discs, dimpled on both sides, which gives them more surface area for oxygen exchange and allows them to squeeze through the tiniest capillaries. Red blood cells are strange among human cells because they lack a nucleus. Most cells have a central command center containing DNA, directing their activities. But red blood cells sacrifice this to make more room for hemoglobin, the oxygen-carrying protein. This makes them efficient carriers, but also means they cannot repair themselves or reproduce. They simply exist for about 120 days, traveling endlessly through the bloodstream before wearing out. Every second, about 2 million red blood cells die in your body, and every second 2 million new ones are born, created in the marrow of your bones. This turnover is constant, seamless, invisible. Right now, even as you rest, your bones are manufacturing fresh cells, replacing the old, maintaining the balance that keeps you alive. The river renews itself continuously, never the same from one moment to the next, yet always constant in its purpose. Each red blood cell will complete a circuit of your entire body in about 1 minute. It will pass through the chambers of your heart thousands of times, visit your lungs thousands of times, deliver oxygen to your brain and muscles and organs over and over, before finally, worn and broken, it is filtered out by the spleen and recycled. Its iron will be saved, used again in new cells. Nothing is wasted. The body is efficient in ways we are only beginning to understand. The breath connection. Blood and breath are inseparable. With every inhalation, oxygen enters your lungs and diffuses across thin membranes into waiting blood. With every exhalation, carbon dioxide that blood has carried from your cells is released back into the air. This exchange happens automatically, thousands of times each day, linking your inner rivers to the atmosphere, to the trees and plants that produce oxygen, to the vast cycles of the living earth. In the lungs, blood flows through millions of tiny capillaries surrounding air sacs called alveoli. The walls here are incredibly thin, just one cell thick, allowing gases to pass through easily. Oxygen molecules slip across the barrier and bind to hemoglobin in red blood cells, 4 oxygen molecules to each hemoglobin protein, filling the cells like tiny balloons being inflated. Once loaded with oxygen, the blood brightens, its color shifting to that brilliant scarlet. It flows back to the heart, which pumps it out through arteries, sending it racing toward tissues that are hungry for oxygen. Cells throughout your body consume oxygen constantly, using it to break down glucose and produce energy. This process, called cellular respiration, is how your cells power themselves, how they perform all the tasks that keep you alive. As cells consume oxygen, they produce carbon dioxide as waste. This diffuses into the blood, which carries it away. The hemoglobin that just delivered oxygen now picks up carbon dioxide, though not in the same way. Some carbon dioxide binds to hemoglobin, some dissolves in the plasma, some converts to bicarbonate ions. All of it flows back toward the heart and lungs, where the cycle begins again. This partnership between blood and breath is ancient. The first animals to evolve circulatory systems did so to solve the problem of oxygen delivery. Single-celled organisms can absorb oxygen directly from their environment, but larger creatures needed a way to transport it to deep tissues. Blood became that solution, and over millions of years, it was refined and perfected into the system that sustains you now. White blood cells, the guardians. Not all cells in blood are red. Scattered among the vast crowds of red blood cells are white blood cells, the guardians and defenders of your body. They are far less numerous, about 1 white cell for every 700 red cells, but their importance cannot be measured by numbers alone. These cells are warriors, detectives, and cleanup crews, all in one. White blood cells are part of your immune system, the defense network that protects you from bacteria, viruses, parasites, and other threats. Unlike red blood cells with their single purpose, white blood cells come in several types, each with specialized roles. Some hunt down and destroy invaders. Some produce antibodies that mark enemies for destruction. Some clean up debris and dead cells. Together, they form a surveillance and response system of extraordinary sophistication. Neutrophils are the most common type, making up about 60% of white blood cells. They are first responders, rushing to sites of infection or injury. When bacteria enter your body through a cut or wound, neutrophils arrive within minutes, drawn by chemical signals. They engulf the invaders, digesting them, sacrificing themselves in the process. The pus that forms at infection sites is largely made up of dead neutrophils, casualties of the battle happening beneath your skin. Lymphocytes are another major type, divided into B cells and T cells. B cells produce antibodies, specialized proteins, that recognize and bind to specific invaders, marking them for destruction. T cells coordinate immune responses and can directly kill infected cells. These cells have memory. Once they encounter a pathogen, they remember it, sometimes for life, allowing faster responses if that same invader returns. This is how vaccines work, training your immune system by showing it safe versions of threats. Monocytes transform into macrophages, large cells that patrol tissues looking for debris, dead cells, and invaders. They are the cleanup crew, constantly working to keep your internal environment clear. Eosinophils and basophils are less common, but important in fighting parasites and in allergic reactions. Each type of white blood cell contributes to the whole, creating a defense system that has evolved over millions of years to counter endless threats. Right now, as you rest peacefully, your white blood cells are working. They are patrolling your bloodstream and tissues, checking for anything unusual, responding to minor infections you may not even notice, maintaining the health you take for granted. They ask nothing of your conscious mind. They simply serve, vigilant and tireless. Platelets, the repair workers. Among the rivers of red and the scattered white cells float tiny fragments called platelets. These are not whole cells, but pieces broken off from larger cells in the bone marrow. They are small, irregularly shaped, and absolutely essential. Without them, even a minor cut could prove fatal. Platelets are responsible for clotting, the process that stops bleeding when blood vessels are damaged. When you cut yourself, platelets are the first to respond. They stick to the edges of the wound, to the exposed collagen fibers beneath the blood vessel lining. They activate and change shape, becoming spiky and sticky, clinging to each other and to the wound. As platelets gather, they release chemical signals that attract more platelets and activate the clotting cascade. This is a complex series of reactions involving dozens of proteins in the blood, each activating the next in sequence. The cascade culminates in the production of fibrin, a protein that forms long strands. These strands weave through the platelet plug, creating a meshwork that traps blood cells and forms a solid clot. The clot acts as both a barrier and a scaffold. It prevents further blood loss and provides structure for tissue repair. Beneath the clot, cells begin dividing and growing, slowly rebuilding the damaged vessel and surrounding tissue. Days later, when healing is complete, the clot is no longer needed. Special enzymes dissolve it, breaking it down and carrying it away. The repair is seamless, the body returning to wholeness. This clotting ability evolved as a crucial survival advantage. Early animals with simple circulatory systems likely died easily from injuries. Those that developed clotting mechanisms survived to reproduce, passing on the genes for this ability. Over time, the system became more refined, more responsive, more reliable. The result is the sophisticated repair network that protects you now. Platelets live for about 10 days before they are removed from circulation. Like red blood cells, they are constantly being replaced, your bone marrow producing about 100 billion new platelets each day. This turnover ensures fresh, functional cells are always available, ready to respond the instant they are needed. Plasma, the forgotten majority. When we think of blood, we usually imagine cells, red and white, traveling through vessels. But cells make up less than half of blood's volume. The majority, about 55%, is plasma, the liquid matrix in which cells are suspended. Plasma is easy to overlook, transparent and seemingly simple, but it is far more than just water-carrying cells. Plasma is about 90% water, but that remaining 10% holds extraordinary complexity. Dissolved in the plasma are proteins, hundreds of different types, each with specific functions. Albumins maintain osmotic pressure, keeping the right balance of fluid between blood and tissues. Globulins include antibodies and transport proteins. Fibrinogen is the precursor to fibrin in clotting. These proteins are constantly at work, performing tasks essential to life. Also dissolved in plasma are nutrients absorbed from your digestive system, glucose for energy, amino acids for building proteins, lipids for cell membranes and signaling. Vitamins and minerals float, here too, being distributed to wherever they are needed. Waste products are carried as well. Urea from protein breakdown, creatinine from muscles, bilirubin from old red blood cells. All of this travels in the plasma, a chemical soup of astonishing complexity. Hormones use plasma as a highway. These chemical messengers, produced by glands throughout your body, need to reach distant targets. Insulin from your pancreas, cortisol from your adrenal glands, thyroid hormones, growth hormones, sex hormones, all travel through plasma, binding to specific receptors on specific cells, triggering specific responses. Through plasma, your body coordinates itself, different organs communicating, different systems synchronizing. Electrolytes maintain the electrical charges necessary for nerve signals and muscle contractions. Sodium, potassium, calcium, and chloride ions exist in precise concentrations, carefully regulated by your kidneys and other organs. Even tiny imbalances can cause serious problems. But normally, these levels stay remarkably stable, the body constantly adjusting, constantly maintaining equilibrium. Gases dissolve in plasma too. Some oxygen and carbon dioxide travel here, not bound to hemoglobin, but simply dissolved. Nitrogen from the air we breathe dissolves in blood and tissues, usually causing no problems, but becoming dangerous in deep-sea divers. If they ascend too quickly, the nitrogen forming bubbles as pressure decreases. Plasma is also the medium of heat distribution. Blood picks up heat from metabolically active tissues like your liver and muscles, and carries it to your skin where it can be released. This temperature regulation keeps your core temperature stable, despite external conditions. When you're too hot, blood vessels in your skin dilate, increasing blood flow and heat loss. When you're cold, they constrict, conserving warmth. All of this happens automatically, blood serving as both coolant and heater. The journey through arteries let us follow blood as it leaves the heart, pushed by the powerful left ventricle into the aorta, the body's largest artery. The surge is strong here, pressure high, the blood moving fast. The aorta arches upward from the heart, then curves down, giving off branches to the head and arms before descending through the chest and abdomen. Arteries are built to handle pressure. Their walls are thick, made of 3 layers, a smooth inner lining, a middle layer of smooth muscle and elastic fibers, and a tough outer coat of connective tissue. The elastic fibers are crucial. They stretch as blood surges with each heartbeat, then recoil, helping to push blood forward even between beats. This gives arteries a pulse, which you can feel wherever an artery runs close to the surface, at your wrist, your neck, your temple. As arteries travel away from the heart, they branch repeatedly, becoming smaller and smaller. The large arteries divide into medium arteries, which divide into small arteries called arterioles. Each division reduces the diameter, but increases the total number of vessels. By the time blood reaches the arterioles, it's flowing through millions of tiny channels, rather than a few large ones. Arterioles are where blood flow is regulated. Their walls contain smooth muscle that can contract or relax, narrowing or widening the vessel. This allows the body to direct blood where it's needed most. During exercise, arterioles in muscles dilate, increasing blood flow to provide more oxygen and nutrients. Arterioles in the digestive system constrict, reducing flow there since digestion isn't immediately necessary. After a meal, the pattern reverses. This distribution is controlled by multiple systems. Nerves send signals to arteriole muscles. Hormones, like adrenaline, cause widespread changes. Local chemical signals from tissues can also affect nearby vessels. A region needing more oxygen releases chemicals that cause local dilation, increasing its blood supply. The whole system is dynamic, constantly adjusting to meet the body's changing needs. Blood pressure is highest in the large arteries and gradually decreases as blood moves through smaller vessels. By the time blood reaches the capillaries, pressure is much lower, gentle enough for the delicate exchange processes that happen there. The pressure drop is caused by friction between blood and vessel walls, and by the resistance of the branching network. The heart must generate enough pressure to overcome this resistance and push blood through the entire circuit. The capillary exchange, the entire circulatory system, exists for what happens in the capillaries. These are the smallest blood vessels, so narrow that red blood cells must squeeze through in single file, their flexible membranes deforming to fit. Capillary walls are just one cell thick, creating the shortest possible distance between blood and tissue. Here, in these microscopic spaces, the essential exchanges occur. There are roughly 40 billion capillaries in the human body, with a total surface area of about 6,300 square meters, roughly the size of a tennis court. Every cell in your body is located within a fraction of a millimeter of a capillary. This proximity is necessary because cells cannot survive far from a blood supply. Oxygen and nutrients can only diffuse short distances before being consumed. In the capillaries, oxygen diffuses out of red blood cells, through the plasma, across the capillary wall, through the interstitial fluid that bathes cells, and finally into the cells themselves. The movement is driven by concentration gradients. Oxygen flows from where it's abundant, in blood, to where it's scarce, in tissue. No energy is required for this diffusion. It's a passive process, nature seeking balance. Simultaneously, carbon dioxide diffuses in the opposite direction from cells where it's produced, through the interstitial fluid, across the capillary wall, and into the blood. Nutrients like glucose and amino acids also exit the blood here, moving into tissues. Waste products from cellular metabolism enter the blood to be carried away. Water also moves across capillary walls, driven by pressure differences and osmotic forces. At the arterial end of capillaries, blood pressure pushes fluid out into tissues. At the venous end, osmotic pressure, created by proteins in blood, draws fluid back in. Most of the fluid returns to the blood, but some remains in tissues and is collected by the lymphatic system, another network of vessels that drains excess fluid and returns it to the bloodstream. This exchange happens continuously, in every tissue, every moment. Your brain, highly active even at rest, receives about 15% of your blood flow, constantly pulling oxygen and glucose from passing blood. Your kidneys, filtering and cleaning blood, receive about 20% of blood flow. Your muscles, at rest, receive relatively little, but during exercise, they can claim up to 80% of the body's blood output. The capillary walls are not uniform. In some organs, they have special features. In the brain, capillaries have very tight junctions between cells, creating the blood-brain barrier that protects delicate neural tissue from toxins. In the liver, capillaries are unusually permeable, allowing for extensive exchange. In the kidneys, capillaries form complex filtering structures. Each specialization suits the organ's particular needs. The return through veins. After passing through capillaries, blood enters venules, small vessels that drain capillary beds and merge into larger veins. The blood here is darker, depleted of oxygen, carrying waste products back toward the heart. Pressure is low now, the driving force of the heartbeat dissipated through the long journey. Blood moves more slowly in veins than arteries, its urgency spent. Veins are different from arteries in structure and function. Their walls are thinner, less muscular, less elastic. They don't need to handle high pressure, so they're built more economically. Many veins, especially in the limbs, contain one-way valves, flaps of tissue that prevent blood from flowing backward. These valves are crucial for returning blood from the legs against gravity. When you walk or move your legs, your muscles contract, squeezing the veins running through them. This compression pushes blood upward. The valves ensure it flows toward the heart, not back down. This is called the skeletal muscle pump, and it's an important assist to circulation. When you sit or stand still for long periods, this pump doesn't operate, and blood can pool in leg veins, causing swelling or discomfort. Breathing helps too. When you inhale, pressure in your chest drops, creating a slight suction that pulls blood toward the heart. The diaphragm moving up and down massages abdominal veins. These mechanical assists compensate for the low pressure in the venous system, ensuring blood returns efficiently. Large veins eventually merge into two major vessels, the superior vena cava, draining the upper body, and the inferior vena cava, draining the lower body. These dump their blood into the right atrium of the heart, completing the circuit. From here, blood is pumped to the lungs to be refreshed, then back to the left side of the heart to begin another journey through the body. The venous system holds most of the body's blood at any given moment, about 60–70% of total volume. Veins act as reservoirs, storing blood that can be mobilized when needed. During exercise or stress, veins constrict slightly, pushing more blood into active circulation, increasing the volume available to working tissues. This reserve capacity is another example of the body's elegant engineering. Blood types, the hidden signatures. On the surface of every red blood cell are proteins and sugars that act as identification markers. These antigens determine your blood type, a genetic signature inherited from your parents. The most important blood type system is ABO, named for the three types of antigens involved: A, B, and neither O. If you have type A blood, your red blood cells carry A antigens. Type B carries B antigens. Type AB carries both. Type O carries neither. Along with these antigens, your plasma contains antibodies against the antigens you don't have. If you're type A, you have anti-B antibodies. If you're type B, you have anti-A antibodies. Type O has both anti-A and anti-B. Type AB has neither antibody. This system is critical for blood transfusions. If someone receives blood with antigens their body recognizes as foreign, their antibodies attack the transfused cells, causing them to clump and break apart. This can be fatal. Type O blood, having no A or B antigens, can be given to anyone in an emergency, making O-negative individuals universal donors. Type AB individuals, having no antibodies against A or B, can receive any blood type, making them universal recipients. The Rh factor is another important blood group system. If you're RR positive, your red blood cells carry the RRRH antigen, also called the D antigen. If you're RR negative, they don't. About 85% of people are Rh positive. This matters especially in pregnancy. If an Rh negative mother carries an Rh positive baby, her immune system might attack the baby's blood cells. Modern medicine prevents this with injections of Rh antibodies. There are actually dozens of blood group systems beyond ABO and Rh, with hundreds of different antigens identified. Most are clinically insignificant, but some can cause problems in transfusions or pregnancies. Blood banks carefully match donors and recipients for the major antigens, and sometimes for minor ones too, to ensure compatibility. Blood types are distributed differently across populations, reflecting human history and migration. Type O is most common globally, possibly because it confers slight advantages against certain diseases like malaria. Type B is more common in Asian populations. Type A is prevalent in Europe. These patterns tell stories of where our ancestors lived and what challenges they faced. Your blood type is just one of countless ways your blood is unique. The exact mix of proteins, the specific antibodies you carry, the mutations in your hemoglobin genes, all of these create a biochemical signature that is yours alone. Your blood is both universally human and individually unique, connecting you to all people while marking you as distinct. The bone marrow factory blood cells don't last forever. Red blood cells wear out after about 4 months. White blood cells and platelets have even shorter lifespans, from days to weeks. To maintain steady numbers, the body must constantly produce new cells, billions every day. This manufacturing happens in the bone marrow, the soft tissue inside many of your bones. In adults, active marrow is found mainly in flat bones, the pelvis, sternum, ribs, vertebrae, and skull. Long bones, like the femur and humerus, contain mainly inactive fatty marrow, though they can reactivate if needed. The marrow is a remarkable factory, housing stem cells that can develop into any type of blood cell. Hematopoietic stem cells are the origin of all blood cells. These rare cells divide to produce both copies of themselves and specialized precursor cells. The precursors further divide and mature, following specific developmental pathways to become red blood cells, white blood cells, or platelets. The process is called hematopoiesis, literally blood making. Red blood cell production is stimulated by a hormone called erythropoietin, produced mainly by the kidneys. When oxygen levels in blood drop, the kidneys detect this and release more erythropoietin, which signals the marrow to make more red blood cells. At high altitudes, where air is thinner and oxygen scarcer, erythropoietin levels increase, leading to more red blood cell production over weeks and months. This is why athletes sometimes train at altitude to boost their oxygen-carrying capacity. White blood cell production is regulated by multiple factors, increasing during infections or stress. The body can ramp up production dramatically when needed, sometimes increasing output several-fold. This is why blood tests during illness often show elevated white blood cell counts. The marrow is working overtime. The marrow is also where B cells mature partially, before migrating to the lymph nodes and spleen for final maturation. T cells begin in the marrow, but migrate to the thymus gland in the chest to mature, which is why they're called T cells. This distribution of immune cell development across multiple organs creates redundancy and specialization. The marrow environment is carefully controlled. Special cells create a niche where stem cells can survive and receive the signals they need. Blood vessels run through the marrow, allowing new cells to enter circulation as soon as they're mature. The whole system is exquisitely regulated, responding to the body's needs, producing exactly what's required. Sometimes marrow can be damaged by disease, radiation, or chemotherapy. When this happens, blood cell production drops, causing anemia, increased infections, and bleeding problems. Bone marrow transplants can save lives in these cases, replacing damaged marrow with healthy stem cells from a donor. The new cells take up residence and begin producing blood, gradually restoring normal function. The spleen, filter, and reservoir, hidden beneath your ribs on the left side, about the size of your fist, lies the spleen. This dark purple organ is part of the lymphatic system, but plays crucial roles in blood health. It is both a filter and a storage depot, constantly monitoring and managing your blood supply. Old red blood cells, after their 120-day lifespan, become less flexible and more fragile. As they pass through the spleen, they must squeeze through narrow passages. Healthy young cells deform easily and pass through. Old cells, too rigid, get stuck. Macrophages in the spleen then engulf and break down these worn-out cells. When red blood cells are destroyed, their components are recycled. The iron from hemoglobin is salvaged and returned to the marrow to be used in new cells. The heme portion is converted to bilirubin, which is sent to the liver and eventually excreted in bile, giving feces its brown color. Nothing is wasted. The body is remarkably efficient at conserving resources. The spleen also serves as a reservoir, holding about a cup of blood in reserve. During exercise, stress, or blood loss, the spleen can contract, releasing this stored blood into circulation. This provides a quick boost to blood volume when needed. In some animals, like horses and dogs, this reservoir function is even more important, allowing rapid increases in oxygen delivery during intense activity. The spleen plays an immune role too. It filters blood for pathogens, removing bacteria, viruses, and parasites. White blood cells in the spleen can respond to blood-borne infections, producing antibodies and destroying invaders. In some ways, the spleen is to the blood what lymph nodes are to tissue fluid, a checkpoint and garrison. People can live without a spleen if it must be removed due to injury or disease. Other organs, primarily the liver, can take over most of its functions. However, people without spleens are more susceptible to certain infections, particularly from encapsulated bacteria, and may need vaccinations and sometimes preventive antibiotics. The liver's role. The liver, the body's largest internal organ, weighs about 3 pounds and sits in the upper right abdomen. It performs hundreds of functions, and many of them involve blood. All blood from the digestive system flows through the liver before returning to the heart, allowing the liver to process nutrients, remove toxins, and monitor for threats. After you eat, nutrients absorbed from your intestines enter the blood and flow directly to the liver via the portal vein. The liver takes up glucose and stores it as glycogen, releasing it later when blood sugar drops. It processes amino acids, building some into proteins, converting others to glucose or fat. It packages fats into lipoproteins for distribution throughout the body. The liver produces many of the proteins found in plasma. Albumin, the most abundant plasma protein, is made exclusively by the liver. So are clotting factors, including fibrinogen and prothrombin. So are complement proteins used by the immune system. Without a functioning liver, these crucial proteins would disappear from the blood within days, causing severe problems. The liver is also the body's primary detoxification center. It breaks down alcohol, drugs, and metabolic waste products, often converting toxic substances into safer forms that can be excreted. Ammonia from protein breakdown is converted to urea, which the kidneys can filter out. Bilirubin from old red blood cells is processed and excreted in bile. Blood flow through the liver is unique. It receives oxygen-rich blood from the hepatic artery like other organs, but it also receives nutrient-rich, oxygen-poor blood from the portal vein, draining the digestive system. This dual supply allows the liver to access both oxygen and nutrients efficiently. The blood mixes in the liver's sinusoids, specialized capillaries, where hepatocytes, liver cells, do their work. The liver can regenerate remarkably well. If part of it is removed or damaged, the remaining tissue can grow and restore function. This regenerative capacity has allowed living liver donation. A person can donate part of their liver to a recipient, and both the donors' and recipients' livers will regrow to nearly normal size. The kidneys, blood's cleaning service. Your kidneys, two bean-shaped organs, about the size of your fist, sit on either side of your spine in the lower back. They receive about 20% of the heart's output, far more blood flow than their size would suggest. This enormous flow is necessary because the kidneys perform the vital task of filtering blood, removing waste while retaining what's needed. Each kidney contains about 1 million nephrons, microscopic filtering units. Blood enters a nephron through a specialized capillary bed called a glomerulus, where pressure forces fluid and small molecules through a filter into a tube. This filtrate contains water, electrolytes, glucose, amino acids, and waste products like urea and creatinine. As filtrate flows through the nephron's tube, useful substances are reabsorbed back into the blood. About 99% of the water is reclaimed, along with all the glucose and amino acids, and most of the sodium and other electrolytes. The remaining fluid, now called urine, contains concentrated wastes and excess water and salts. This urine flows to the bladder for storage and eventual excretion. The kidneys regulate blood pressure by controlling blood volume. If you drink a lot of water, your kidneys excrete the excess, keeping blood volume stable. If you're dehydrated, they conserve water, producing concentrated urine. They also secrete a hormone called renin when blood pressure drops, which triggers a cascade that raises pressure and restores flow. The kidneys maintain electrolyte balance with precision. They adjust how much sodium, potassium, calcium, and other ions are retained or excreted, keeping blood concentrations within narrow ranges. They also regulate blood pH by controlling how much acid or base is excreted. These balancing acts are crucial because many cellular processes depend on stable chemical conditions. The kidneys produce erythropoietin, the hormone that stimulates red blood cell production. They sense oxygen levels in blood and respond by adjusting erythropoietin output. This links kidney function to oxygen delivery throughout the body, showing how interconnected our systems truly are. Kidney disease can severely affect blood health. When kidneys fail, waste products accumulate in blood, causing uremia, a toxic condition. Erythropoietin production drops, causing anemia. Fluid balance becomes disturbed, leading to swelling and high blood pressure. Dialysis, which mechanically filters blood, can substitute for kidney function, but it's only a partial replacement for these remarkable organs. Blood pressure, the force of flow. Blood pressure is the force blood exerts against vessel walls as it flows. It's created primarily by the heart's pumping action and maintained by the resistance of arterioles. Blood pressure is measured in millimeters of mercury and given as two numbers: systolic pressure during heart contraction over diastolic pressure during heart relaxation. Normal adult blood pressure is around 120/80. Pressure must be high enough to drive blood through the entire circulatory system, reaching all tissues with adequate flow. But if pressure is too high, it strains the heart and damages blood vessels. Hypertension, chronically elevated blood pressure, is called the silent killer because it often causes no symptoms but increases risk of heart attack, stroke, and kidney disease. Blood pressure varies throughout the circulatory system. It's highest in the aorta, where blood first exits the heart and gradually decreases as blood flows through smaller vessels. By the time blood reaches veins, pressure is very low, close to zero. This pressure gradient drives flow, blood always moving from high pressure to low pressure areas. Many factors affect blood pressure. Heart rate and strength of contraction, obviously, matter. A stronger, faster heart generates more pressure. Blood volume is crucial too. Losing blood through injury drops pressure, while retaining too much fluid raises it. The diameter of arterioles is perhaps most important for moment-to-moment regulation. When they constrict, resistance increases and pressure rises throughout the system. The body regulates blood pressure through multiple mechanisms. Baroreceptors in major arteries sense pressure changes and send signals to the brain, which adjusts heart rate and vessel diameter accordingly. Hormones like adrenaline raise pressure during stress. The renin-angiotensin system, involving kidneys and several hormones, provides longer-term control. Blood pressure changes with activity and emotion. During exercise, systolic pressure increases to meet muscle demands, sometimes reaching 200 or higher in healthy people. During sleep, pressure drops by 10–20%, giving the cardiovascular system rest. Stress and anxiety raise pressure temporarily. These fluctuations are normal and healthy. Position affects pressure too, because of gravity. When you stand up quickly, blood pools in your legs, temporarily reducing the amount returning to your heart. Blood pressure in your brain can drop, causing dizziness or even fainting. Healthy reflexes quickly constrict veins and increase heart rate to compensate. But sometimes they're too slow, especially in elderly people or those with certain conditions. The clotting cascade, a molecular symphony. When a blood vessel is damaged, the body must respond quickly to prevent excessive blood loss. The clotting process is a cascade of reactions, each step triggering the next, rapidly amplifying the response. It's a molecular symphony, with dozens of proteins playing precisely timed parts. The cascade has two pathways, intrinsic and extrinsic, which converge into a common pathway. The extrinsic pathway is triggered by tissue factor, a protein exposed when blood vessels are damaged. It initiates quickly, within seconds. The intrinsic pathway is activated by contact with damaged vessel surfaces and takes longer to develop but provides sustained clotting. Both pathways activate factor X, a key protein in the common pathway. Activated factor X converts prothrombin to thrombin, and thrombin converts fibrinogen to fibrin. Fibrin molecules link together, forming long threads that weave through the platelet plug, creating a stable mesh. Red blood cells and more platelets get trapped in this mesh, forming a solid clot. Thrombin also activates more platelets and triggers positive feedback, producing more thrombin. This amplification is why clotting accelerates rapidly once started. A small initial stimulus can produce a large response very quickly, which is exactly what's needed to seal wounds. But clotting must be controlled. Clots forming in intact blood vessels would be dangerous, potentially blocking blood flow and causing heart attacks or strokes. Multiple mechanisms prevent inappropriate clotting. Healthy vessel linings actively resist clot formation. Blood flow disperses clotting factors before they can accumulate, and the blood contains natural anticoagulants, proteins that inhibit clotting factors. The most important natural anticoagulant is antithrombin, which inactivates thrombin and several other clotting factors. Protein C and protein S work together to degrade active clotting factors. These inhibitors ensure clotting only occurs where needed. Once a wound heals, clots must be removed. This happens through fibrinolysis, the breakdown of fibrin. The key enzyme is plasmin, which cuts fibrin strands. Plasminogen, the inactive precursor, is incorporated into clots as they form. Later, tissue plasminogen activator, converts plasminogen to plasmin within the clot, slowly dissolving it from within. Clotting disorders can be devastating. Hemophilia is a genetic condition where one clotting factor is missing or deficient, making it difficult to form stable clots. People with hemophilia can bleed severely from minor injuries and suffer from spontaneous internal bleeding. Treatment involves infusing the missing factor. Other disorders cause excessive clotting, increasing risk of thrombosis. These may be treated with anticoagulant medications. Hemoglobin, the oxygen carrier. At the molecular level, the oxygen-carrying capacity of blood comes down to hemoglobin, a protein of elegant complexity. Each hemoglobin molecule consists of 4 protein chains, 2 alpha and 2 beta, each wrapped around a heme group containing iron. The iron atom is what actually binds oxygen. When oxygen binds to one heme group, it causes a shape change in the hemoglobin molecule that makes it easier for oxygen to bind to the other heme groups. This is called cooperative binding, and it means hemoglobin's oxygen affinity increases as more oxygen attaches. This property allows hemoglobin to pick up oxygen efficiently in the lungs and release it efficiently in tissues. The relationship between oxygen concentration and hemoglobin saturation forms a shaped curve called the oxygen-hemoglobin dissociation curve. In the lungs, where oxygen concentration is high, hemoglobin becomes nearly fully saturated, each molecule carrying 4 oxygen molecules. In tissues, where oxygen concentration is lower, hemoglobin releases oxygen. Several factors affect how tightly hemoglobin holds onto oxygen. Higher temperature, lower pH, and higher carbon dioxide concentration all cause hemoglobin to release oxygen more readily. These conditions exist in metabolically active tissues, so hemoglobin automatically delivers more oxygen where it's needed most. This is called the Bohr effect. Carbon dioxide affects oxygen binding in another way too. Some carbon dioxide reacts with hemoglobin directly, forming carbaminohemoglobin. This lowers hemoglobin's oxygen affinity, promoting oxygen release. Meanwhile, carbon dioxide that dissolves in blood forms carbonic acid, lowering pH, which also reduces oxygen affinity. These mechanisms ensure efficient oxygen delivery and carbon dioxide removal. Fetal hemoglobin has a slightly different structure than adult hemoglobin, with 2 gamma chains instead of 2 beta chains. This gives it higher oxygen affinity, allowing it to pull oxygen from maternal blood in the placenta. After birth, production switches to adult hemoglobin over several months. Some genetic variations in hemoglobin have significant effects. Sickle cell anemia results from a single amino acid change in the beta chains. This causes hemoglobin molecules to stick together when deoxygenated, forming long fibers that distort red blood cells into sickle shapes. These cells are fragile and can block small blood vessels, causing pain and tissue damage. Interestingly, carrying one sickle cell gene, being a carrier but not having the disease, provides some protection against malaria, which is why the gene remains common in populations from malaria-prone regions. This is a classic example of balanced selection, where a harmful mutation persists because carriers have an advantage. Blood sugar, energy and circulation. Glucose is the primary fuel for most cells, and blood is the delivery system. After you eat carbohydrates, they're broken down to simple sugars and absorbed into blood. Blood glucose levels rise, triggering the pancreas to release insulin, a hormone that signals cells to take up glucose. Muscle and liver cells store excess glucose as glycogen. Fat cells convert it to fat for long-term storage. Between meals, as cells consume glucose, blood levels drop. The pancreas responds by releasing glucagon, which signals the liver to break down glycogen and release glucose. This maintains relatively stable blood glucose levels throughout the day, typically between 70 and 100 milligrams per deciliter when fasting. The brain is particularly dependent on glucose. Unlike muscles, which can burn fat, the brain relies almost exclusively on glucose for energy. It consumes about 20% of the body's glucose, despite being only 2% of body weight. If blood glucose drops too low, brain function is affected, causing confusion, dizziness, and if severe, loss of consciousness. Diabetes mellitus is a disease of blood glucose regulation. In type 1 diabetes, the immune system destroys the pancreatic cells that produce insulin, so blood glucose can't be controlled. In type 2 diabetes, cells become resistant to insulin, requiring higher levels to achieve the same effect. In both cases, blood glucose remains chronically elevated, which damages blood vessels, nerves, and organs over time. High blood glucose is toxic to blood vessels. It causes chemical changes in vessel walls, promotes inflammation, and encourages atherosclerosis, the buildup of plaques that narrow arteries. This is why diabetics have increased risk of heart disease, stroke, kidney failure, and circulation problems in the extremities. Managing blood glucose through diet, exercise, and medication can prevent or delay these complications. Blood glucose monitoring has become much easier with modern technology, allowing diabetics to track their levels throughout the day and adjust treatment as needed. The inflammatory response. When tissues are injured or infected, blood is central to the inflammatory response. Damaged cells and invading microbes trigger chemical signals that affect nearby blood vessels. Arterioles dilate, increasing blood flow to the area, causing redness and warmth. Capillaries become more permeable, allowing fluid and proteins to leak into tissues, causing swelling. This increased permeability also allows white blood cells to exit blood vessels more easily. Neutrophils are first to arrive, squeezing between capillary cells in a process called diapedesis. Chemical attractants guide them to the site of damage or infection. They engulf bacteria and debris, helping to clean the wound. Monocytes arrive later and transform into macrophages, continuing the cleanup and coordinating later stages of healing. These cells also release chemical signals that attract more immune cells and stimulate tissue repair. The whole process is carefully orchestrated, with different cell types playing different roles at different times. Inflammation is protective, part of healing, but chronic inflammation can be harmful. If inflammation persists, it can damage healthy tissue. Autoimmune diseases involve inappropriate inflammation attacking the body's own cells. Chronic inflammatory conditions like rheumatoid arthritis and inflammatory bowel disease can be debilitating. Many medications target inflammation. Aspirin and ibuprofen block enzymes that produce inflammatory mediators. Corticosteroids broadly suppress immune responses. Newer biologics target specific inflammatory molecules. These drugs help control symptoms but can have side effects, particularly with long-term use. Blood and disease detection. Blood tests are among medicine's most valuable diagnostic tools. Because blood touches every tissue, changes in its composition can reflect disease throughout the body. A complete blood count measures different cell types, revealing anemia, infections, or blood cancers. A metabolic panel measures glucose, electrolytes, and kidney function markers. Liver function tests measure enzymes and proteins produced by the liver. Specific tests can detect particular conditions. Troponin, a protein from damaged heart muscle, rises during heart attacks. PSA screening for prostate cancer, CA 125 for ovarian cancer, and many other tumor markers can be measured in blood. Tests for infectious diseases detect either the pathogen itself or antibodies against it. Blood tests can also monitor treatment. Diabetics check blood glucose regularly. People on blood thinners have clotting times monitored. Cancer patients have tumor markers measured to assess whether treatment is working. The ability to sample blood easily and repeatedly makes it ideal for ongoing monitoring. Advances in blood testing continue. Liquid biopsies can detect tumor DNA circulating in blood, potentially allowing early cancer detection or monitoring for recurrence. Multi-cancer early detection tests aim to screen for multiple cancer types with a single blood draw. Technology is making blood tests faster, cheaper, and more informative. Blood donation, the gift of life. Blood cannot be manufactured. When it's needed for surgery, trauma, or disease treatment, it must come from donors. Blood donation is one of the simplest and most direct ways to save lives. A single donation can help multiple patients, as whole blood can be separated into red cells, plasma, and platelets, each used for different purposes. The donation process is straightforward and safe. Donors are screened for eligibility, ensuring they're healthy enough to donate, and their blood will be safe for recipients. A pint of blood is collected, taking about 10 minutes. The body replaces the fluid within hours, and the cells within weeks. Most donors experience no side effects beyond perhaps mild fatigue. Donated blood is tested for infections including HIV, hepatitis, and others. It's typed for ABO and RH. Then it's separated into components or kept as whole blood, depending on need. Red cells are refrigerated and last about 42 days. Platelets must be kept at room temperature and agitated, lasting only 5 days. Plasma can be frozen and stored for years. Blood is used in many situations. Trauma patients may need massive transfusions, receiving dozens of units. Surgical patients may need several units to replace blood lost during procedures. Cancer patients may need red cells to treat anemia from chemotherapy or platelets if their counts drop. Patients with blood disorders like sickle cell disease may need regular transfusions throughout their lives. There's always need for blood donors. Demand is constant while donation rates fluctuate. Type O negative blood is especially valuable because it can be given to anyone in emergencies before the patient's type is known. Regular donors, giving multiple times per year, are the backbone of the blood supply. Some people donate specific components through apheresis, where blood is drawn, the desired component separated out, and the rest returned. Platelet donors can give every few days. Plasma donors can give twice a week. These donors provide crucial resources for patients needing large amounts of specific components. Blood doping and manipulation. Because blood carries oxygen, increasing oxygen carrying capacity can enhance athletic performance. This led to various forms of blood doping, practices aimed at artificially boosting red blood cell counts or oxygen delivery. Some methods are illegal in competitive sports, others are ethically questionable. The simplest form is altitude training. Training at high altitude stimulates natural production of red blood cells. When athletes return to sea level, they temporarily have extra oxygen carrying capacity, potentially improving endurance. This is legal and commonly used. Blood transfusion doping involves removing and storing an athlete's own blood, allowing the body to replace it, then transfusing it back before competition. This temporarily increases red cell count above normal. It's banned in most sports, but difficult to detect if it's the athlete's own blood. Erythropoietin, EPO. Doping involves taking synthetic EPO to stimulate red cell production. EPO is normally used medically to treat anemia in kidney disease patients. Athletes abused it for performance enhancement, particularly in cycling. Testing methods eventually developed to detect synthetic EPO, but newer versions continue to appear. Blood doping is dangerous. Excessive red blood cells make blood thicker, increasing risk of clots, strokes, and heart problems. Several athletes have died from complications of blood doping. The pursuit of competitive advantage can override safety considerations, with tragic results. Sports organizations continually update testing to detect new doping methods. The biological passport system tracks athletes' blood parameters over time, flagging unusual changes that might indicate doping even if specific banned substances can't be detected. It's an ongoing arms race between dopers and testers. Evolution of blood. Blood didn't appear suddenly, but evolved over millions of years. The earliest animals were simple, small enough for oxygen to diffuse directly to their cells. As animals grew larger and more complex, they needed specialized systems for oxygen delivery. The first circulatory systems were simple, open cavities, where hemolymph, the invertebrate equivalent of blood, bathed tissues directly. Closed circulatory systems, where blood stays in vessels, evolved independently in several lineages. They're more efficient, allowing better control of flow and pressure. Vertebrates, including humans, have closed circulatory systems with hearts, arteries, capillaries, and veins. The heart itself evolved from simple tubes in early fish to the four-chambered organs in mammals and birds. Fish hearts have two chambers and pump blood in a single circuit, heart to gills to body to heart. Amphibians and reptiles have three chambers, with some mixing of oxygenated and deoxygenated blood. Mammals and birds have four chambers, with complete separation, maximizing efficiency. Hemoglobin evolved from ancient proteins that could bind oxygen. The four-chain structure of human hemoglobin arose through gene duplications and modifications. Different animals have adapted hemoglobin to their needs. Diving mammals have hemoglobin with very high oxygen affinity, allowing them to store oxygen for long dives. Animals living at high altitudes have versions that work well in low oxygen conditions. Blood clotting evolved as animals developed circulatory systems. Early mechanisms were simple. Over time, the cascade became more complex, with multiple pathways and controls. This sophistication reflects the importance of balanced clotting, enough to prevent death from bleeding, but not so much that spontaneous clots form. The immune functions of blood also evolved over time. Invertebrates have simple immune responses. Vertebrates developed adaptive immunity with T cells, B cells, and antibodies, allowing specific responses to specific threats and immunological memory. This gives humans and other vertebrates powerful protection against diverse pathogens. Blood in culture and history. Blood has always held special significance in human cultures. Its association with life and death, its dramatic appearance when spilled, its warmth and movement all made it powerful symbolically. Ancient peoples sometimes believed blood contained the soul or life force. Blood sacrifice appears in many ancient religions, offering blood to gods to ensure favor, good harvests, or victory. Animal sacrifice was common, human sacrifice less so, but practiced in some cultures. These rituals reflected the belief that blood had special power, that its offering carried weight. Blood oaths and blood brotherhood ceremonies bonded individuals or groups. Sharing blood was seen as creating a connection stronger than ordinary agreements. Bloodlines determined inheritance and social status. Blue blood for aristocracy came from pale skin showing blue veins, distinguishing nobility from sun-darkened peasants. Many taboos surrounded blood, particularly menstrual blood. Women were sometimes considered unclean during menstruation, excluded from religious rites or social activities. These taboos reflect both fear of blood and misunderstanding of female biology. Blood revenge, where family members avenged killings, drove many historical conflicts. The phrase, "blood is thicker than water," reflects the primacy of family bonds. Blood feuds could last generations, with each death demanding another in retaliation. Medicine long misunderstood blood. The ancient Greeks believed health depended on balancing four humors: blood, phlegm, yellow bile, and black bile. Bloodletting, deliberately removing blood to treat disease, was practiced for thousands of years. It was useless at best, harmful at worst, but persisted until the 19th century, when scientific medicine began understanding blood's true nature. Blood transfusion was attempted for centuries, with universally fatal results, until Karl Landsteiner discovered blood types in 1901. Understanding compatibility made transfusions safe and practical, saving countless lives in warfare and medicine. Today, blood retains cultural significance. Blood still means family in many contexts. Vampires, mythical creatures drinking blood for sustenance, remain popular in fiction. Seeing blood still provokes strong reactions in most people, a reminder of its deep psychological impact. Blood and identity. Modern forensics uses blood extensively. Blood type can help include or exclude suspects. DNA from white blood cells provides unique identification, solving crimes and paternity disputes. Blood spatter analysis can reconstruct violent events, showing what happened through the patterns blood makes when shed. Blood carries information about ancestry. Different populations have different frequencies of blood types and genetic markers. While race is not a biological category, population genetics can trace heritage through blood. This has been used to study human migration patterns and history. In medicine, blood increasingly reveals individual characteristics. Genetic tests on blood can identify risk factors for diseases, predict drug responses, and detect genetic disorders. The emerging field of precision medicine aims to tailor treatment based on individual genetic profiles revealed through blood testing. Blood banking has created databases of millions of people's blood information. While this is primarily medical, it raises privacy concerns. Who has access to this information? How is it protected? Can it be used for non-medical purposes? These questions become more urgent as blood testing becomes more comprehensive and informative. Cord blood banking preserves stem cells from umbilical cord blood after birth. These cells might treat future diseases in the child or family members. Private banks charge fees. Public banks accept donations. The science is promising but controversial regarding the actual likelihood these cells will be needed. Artificial blood. The quest continues. Developing artificial blood has been a goal for decades. The benefits would be enormous. Unlimited supply, no disease transmission, no need for type matching, long shelf life. Despite intensive research, success has been limited. The main challenge is recreating hemoglobin's oxygen-carrying function. Free hemoglobin is toxic. It must be contained or modified. Early attempts used hemoglobin from expired donated blood or cow blood, chemically modified to be safer. These products could carry oxygen, but had problems: toxicity, short duration, constriction of blood vessels. Perfluorocarbon emulsions are chemicals that dissolve large amounts of oxygen. They can temporarily substitute for red blood cells, delivering oxygen to tissues. Some have been approved for specific uses, but they're not true blood replacements. They don't carry carbon dioxide well, and they're eventually exhaled through the lungs. requiring repeated administration. Stem cell approaches aim to grow red blood cells in laboratories. Starting with stem cells, researchers can induce them to become red blood cells. This has been done successfully in small amounts. The challenge is scaling up production to clinically useful quantities at reasonable cost. As technology improves, this approach becomes more feasible. Hemoglobin-based oxygen carriers, HBOCs, modify hemoglobin molecules to be stable and safe outside red blood cells. Some are derived from human hemoglobin, others from animal sources, or are entirely synthetic. Several have been tested clinically, with mixed results. Some showed efficacy, but also side effects, including increased heart problems. No artificial blood product has yet achieved widespread use. Donated human blood remains the standard. Research continues because the potential benefits are so great. Perhaps future technology will create true artificial blood, but for now, the natural version remains irreplaceable. Blood disorders. Many diseases affect blood. Anemias involve reduced red blood cells, or hemoglobin. Iron deficiency anemia, the most common, results from insufficient iron to make hemoglobin. Vitamin B12, or folate deficiency, can impair red cell production. Hemolytic anemias involve premature red cell destruction. Sickle cell disease and thalassemias are inherited hemoglobin disorders. Sickle cell causes red cells to deform and break down. Thalassemias involve reduced production of hemoglobin chains. Both can cause severe anemia and complications. Treatment ranges from supportive care to transfusions to bone marrow transplant. Leukemias are cancers of white blood cells. Abnormal white cells proliferate in bone marrow, crowding out normal blood cell production. Acute leukemias progress rapidly. Chronic forms develop slowly. Treatment involves chemotherapy, sometimes stem cell transplantation. Prognosis varies greatly depending on type and patient factors. Lymphomas are cancers of lymphocytes that typically start in lymph nodes, but can affect blood. Multiple myeloma is a cancer of plasma cells, antibody-producing cells related to B lymphocytes. These blood cancers are treated with various combinations of chemotherapy, radiation, and transplantation. Clotting disorders include hemophilia, deficiency of clotting factors causing bleeding, and thrombophilias, increased clotting tendency causing dangerous clots. Von Willebrand disease affects platelet function and clotting. These disorders range from mild to life-threatening. Immune thrombocytopenia involves antibodies destroying platelets, causing low platelet counts and bleeding risk. Aplastic anemia involves bone marrow failure, reducing all blood cell types. These conditions require careful management, sometimes including immunosuppressive treatment. Many blood disorders can now be managed effectively with modern medicine, though some remain challenging. Research continues to develop better treatments, including gene therapy for inherited disorders. The future of blood medicine. Medicine's relationship with blood continues evolving. Liquid biopsies may revolutionize cancer detection and monitoring. Instead of tissue biopsies requiring surgery, blood tests could detect tumors early through circulating tumor DNA or cells. This could catch cancers when they're most treatable. Personalized medicine will increasingly use blood tests to guide treatment. Genetic profiles from blood will predict which drugs work best for which patients. Monitoring of treatment responses through blood biomarkers will become more sophisticated, allowing real-time adjustment of therapy. Artificial intelligence is being applied to blood testing. Machine learning can find patterns in blood data that humans miss, potentially diagnosing diseases earlier or predicting outcomes more accurately. AI might someday analyze blood results faster and more accurately than human physicians. Gene therapy delivered through blood is being developed. Modified viruses carrying corrective genes can be injected into blood, reaching cells throughout the body. This approach has shown promise for inherited blood disorders and other conditions. CRISPR gene editing might allow direct editing of genes in blood cells or stem cells. This could cure genetic diseases by correcting the faulty genes causing them. Early trials are underway for sickle cell disease and thalassemia, with promising initial results. Improved blood storage and preservation techniques are being developed. If blood could be stored longer or frozen more effectively, it would improve blood banking logistics. Artificial blood research continues, and perhaps within decades, practical substitutes will emerge. Understanding of blood's role in aging is growing. Some research suggests young blood has rejuvenating properties, while old blood may accelerate aging. This raises the possibility of blood-based anti-aging treatments, though much more research is needed. Blood connection to every system. Blood's relationship with other body systems is intimate and essential. The respiratory system and blood are partners, exchanging gases in the lungs. The digestive system feeds nutrients into blood for distribution. The urinary system filters waste from blood and regulates its composition. The endocrine system uses blood as a communication network. Hormones travel through blood to reach distant targets, coordinating activities throughout the body. Blood glucose regulation, stress responses, growth, reproduction, all depend on hormones in blood. The nervous system and blood interact constantly. Nerves control blood vessel diameter, heart rate, and blood distribution. The blood-brain barrier protects neural tissue while allowing necessary exchange. Some areas of the brain directly sense blood composition, monitoring glucose, oxygen, and other factors. The immune system lives partly in blood, with white blood cells patrolling and responding to threats. Lymphatic circulation is closely tied to blood circulation, draining tissues and returning fluid to blood. The integumentary system, skin, receives blood flow that regulates temperature. Blushing and blanching reflect blood vessel changes. Skin appearance often reflects blood health, pale in anemia, jaundiced in liver disease, cyanotic in poor oxygenation. The skeletal system houses the marrow that produces blood cells. Bone health and blood health are connected. The muscular system, especially the heart, drives blood circulation. Skeletal muscle activity assists venous return. Everything in the body is connected through blood. It's the ultimate common pathway, the medium through which different organs and systems communicate and cooperate. Understanding any body system requires understanding its relationship to blood. The microscopic world within. If you could shrink down and swim through blood, you'd find yourself in a crowded river. Red blood cells would surround you, millions of biconcave discs tumbling in the flow. They'd brush past, flexible and soft, deforming to squeeze through narrow passages. White blood cells would be rarer but dramatic when encountered. Neutrophils with their multi-lobed nuclei, lymphocytes with their large round nuclei, monocytes preparing to transform. You might see one attached to a vessel wall, squeezing between cells to exit into tissue. Platelets would appear as tiny fragments, much smaller than red cells, some clustered where vessel walls are damaged. You'd see the fibrin strands they create, weaving through clots like spider silk. The plasma would be the medium you swim through, clear and slightly yellowish. You wouldn't see the dissolved molecules, glucose, ions, proteins, hormones, but they'd be there, creating the chemical environment that sustains life. Traveling through an artery, you'd feel the surge of pressure with each heartbeat, the vessel wall stretching and recoiling. The current would be swift, carrying you rapidly forward. In capillaries, the pace would slow. The vessels would narrow, until red cells must pass single file. The walls would be thin, and you'd see oxygen diffusing outward, carbon dioxide diffusing inward, nutrients leaving, wastes entering. In veins, the pressure would be low, the flow slower and steadier. You'd see valves opening as blood flows toward the heart, snapping shut to prevent backflow. You'd pass through the heart chambers, feeling the powerful contractions that squeeze blood forward. In the lungs, you'd witness the gas exchange, oxygen flooding in, carbon dioxide streaming out. Throughout the journey, you'd sense the organization, the purpose behind each structure. Everything serves the function of delivery and collection, of maintaining the internal environment that allows life to continue. The warmth of lifeblood carries heat. Your core temperature, normally about 98.6 degrees Fahrenheit, 37 degrees Celsius, is maintained partly through blood circulation. Metabolically active organs like the liver and working muscles generate heat, which blood absorbs and distributes. When you're cold, blood vessels in your skin constrict, reducing blood flow to the surface and conserving heat. Your core stays warm, even as your extremities cool. When you're hot, skin vessels dilate, increasing flow and heat loss. Sweating further cools the blood flowing through skin. This temperature regulation happens automatically, controlled by the hypothalamus in the brain. It constantly monitors blood temperature and adjusts blood flow, sweat production, and other factors to maintain stability. Fever is a controlled increase in body temperature, usually in response to infection. Hypothalamus resets its target temperature higher, and the body works to reach it. Blood carries heat from metabolically active tissues, raising temperature throughout the body. The elevated temperature may help fight infection by enhancing immune function and inhibiting pathogen growth. Extreme temperatures can overwhelm regulation. Hypothermia occurs when body temperature drops too low, slowing metabolism and potentially causing death. Hypothermia, excessive heating, can denature proteins and damage cells. Blood temperature is carefully guarded because so many biological processes depend on it. The warmth of blood is life itself. When people die, their bodies cool as blood stops flowing. Metabolic heat generation ceases, and temperature equalizes with the environment. The phrase cold-blooded for reptiles and fish refers to their inability to regulate body temperature. Internally, their blood temperature varies with their environment. Warm-blooded mammals and birds maintain constant temperature, and blood is central to this ability. Blood as metaphor. Beyond its biological reality, blood permeates language and thought. We speak of bloodlines, bloodshed, blood feuds. We call close relatives blood relations. A cruel person is cold-blooded. An exciting event gets blood pumping. In literature, blood often symbolizes life, death, guilt, or passion. Lady Macbeth's imagined bloodstains represent guilt that cannot be washed away. Blood oaths in fiction create unbreakable bonds. Vampires drinking blood represent various themes: sexuality, immortality, predation, or corruption. Political rhetoric uses blood imagery. Blood and soil nationalism connects people to land through ancestry. Blood sacrifice for the nation honors those who died in service. These metaphors pack emotional power because blood literally means life. Religious traditions often incorporate blood symbolism. Christian communion involves wine representing Christ's blood. Jewish dietary laws prohibit consuming blood, considering it sacred. Many cultures have rituals involving blood, recognizing its significance. The power of blood metaphors comes from its concrete reality. Everyone has seen blood, knows its appearance and meaning. When used symbolically, it carries that visceral weight. Blood is not abstract. It's vividly real, making it effective for conveying intense emotions or ideas. The poetry of flow. There is something almost meditative about imagining blood's journey. The endless circulation, the quiet persistence, the perfect organization of millions of components working together. Each cell knows its role, each protein performs its function, all without conscious direction. Your heart beats now, has beaten more than 2 billion times in your life. If you're middle-aged, will beat billions more. Blood flows, has flowed, will flow, as long as life continues. This is the fundamental rhythm of existence, underlying everything else you do, think, or feel. Consider the cooperation required. Red cells, made in bone marrow, travel to lungs, pick up oxygen, deliver it to tissues, return to lungs. White cells patrol constantly, ready to respond. Platelets wait dormant until needed, then act instantly. Plasma carries everything, provides the medium for exchange, maintains the chemical environment. The vessels form a network of extraordinary complexity, branching and converging, sized perfectly to match function. The heart pumps steadily, adjusting output to meet demand. Organs filter, modify, and monitor blood, keeping it healthy. All of this happens in darkness, in silence, without conscious thought. You don't have to remember to make blood cells or regulate blood pressure. You don't consciously direct clotting or immune responses. The body simply does it, automatically, based on information encoded in genes and refined through millions of years of evolution. This is the quiet miracle of biology. Life sustaining itself through countless microscopic actions, organized into patterns that maintain the whole. Blood is perhaps the clearest example of this organization, this cooperation, this elegant complexity. The soothing rhythm. As you rest now, your blood continues its ancient dance. Feel it if you can, the gentle pulse at your wrist, your neck, your temple. This is the rhythm of life itself, steady and sure. With each beat, blood surges forward, carrying oxygen and nutrients, removing wastes, maintaining the delicate balance that keeps you alive. This rhythm has lulled countless humans before you into sleep. It's the first sound you heard in the womb, your mother's heartbeat and your own, intertwined. It's the last sound that will fade as life ends. Between birth and death, it continues, mostly unnoticed, always faithful. There's a comfort in this constancy. While everything else in life changes, while thoughts tumble and emotions shift, blood keeps flowing. Your heart keeps beating. The river within keeps moving, asking nothing, giving everything. Let this rhythm soothe you now. Breathe slowly, feeling your heartbeat slow in response. Each breath brings oxygen to blood. Each heartbeat sends it through your body. The cycle is automatic, reliable, requiring nothing from your conscious mind. Blood and sleep. Sleep itself is connected to blood. As you drift towards sleep, your blood pressure drops slightly. Your heart rate slows. Blood flow to the brain changes. These cardiovascular changes are part of the transition from wakefulness to rest. During deep sleep, growth hormone is released into blood, promoting tissue repair and growth. This is when your body does much of its healing and maintenance. Blood delivers these hormones and the nutrients needed for repair to tissues throughout your body. Sleep affects blood in other ways too. People who don't sleep enough tend to have higher blood pressure, elevated stress hormones, and increased inflammation markers in their blood. Chronic sleep deprivation affects blood sugar regulation, increasing diabetes risk. Good sleep supports blood health. Some sleep disorders involve blood directly. Sleep apnea, where breathing repeatedly stops during sleep, causes oxygen levels in blood to drop repeatedly. This stresses the cardiovascular system and can lead to high blood pressure and heart problems. Treatment improves not just sleep quality, but blood oxygen levels and cardiovascular health. As you settle into sleep tonight, your blood is preparing for its nighttime routine. Flow to digestive organs increases slightly if you ate before bed, supporting digestion. Flow to skin may increase, allowing heat loss to lower core temperature slightly, which promotes deep sleep. Flow to muscles decreases as they relax. Flow to the brain changes in complex ways, supporting the neural activity of dreaming. All of this happens without your awareness. Blood continues its work, supporting your body through the vulnerable time of sleep, ensuring you wake, refreshed and restored. The ancient river blood predates humanity. Animals have had blood for hundreds of millions of years. The basic pattern, a pump, vessels, oxygen carriers, immune cells, was established long before humans evolved. In a very real sense, the blood flowing through you is ancient, its design refined over eons. Your blood connects you to your ancestors, not just metaphorically but literally. The genes that determine your blood type came from your parents, who inherited them from their parents, back through countless generations. Some of those genes are so old they're shared with other primates, with other mammals, even with much more distant relatives in the animal kingdom. The chemistry of your blood resembles that of other mammals closely. The differences are subtle, refinements and adaptations to particular ways of life. But the fundamental patterns are shared, evidence of common ancestry, of the deep connections between all life. When you look at blood under a microscope, you see the same basic cells humans have observed for over a century. The first person to see blood cells through a microscope saw what you would see today: the countless red discs, the rarer white cells, the tiny platelets. These structures haven't changed in the brief time. Humans have been studying them, and they won't change in your lifetime or your descendants' lifetimes. There's something humbling about this deep time perspective. Your individual blood cells live briefly, weeks or months. But the pattern of blood, the system itself, has existed for geological ages and will continue long after you're gone. You are a temporary vessel for this ancient river, hosting it briefly before passing it on. Individual uniqueness. Yet while blood is ancient and universal, your blood is also uniquely yours. Your specific blood type, the precise mix of antibodies you carry, the mutations in your DNA, all of these make your blood distinct from everyone else's except perhaps an identical twin. Blood tests can identify you specifically. DNA from your white blood cells is unique to you, different from all other humans. This is useful in medicine, allowing personalized diagnosis and treatment. It's useful in forensics, identifying people from blood evidence. But it also means your blood carries your identity, is part of who you are. Your blood also reflects your experiences. If you've been infected with certain viruses, you carry antibodies to them, sometimes for life. Your blood remembers these encounters, will respond faster if they occur again. If you've been vaccinated, the evidence is in your blood. If you've traveled to high altitude, adapted to dietary changes, or experienced pregnancy, your blood has changed in response. In this sense, blood is a record of your life, carrying molecular memories of where you've been and what you've experienced. It's shaped by your genes, but also by your environment, your choices, your circumstances. Your blood is both inherited and created, both ancient and new, both universal and unique. The gift you've received. You did not create your blood. It was given to you, developed before you were born, maintained since then by biological systems you don't consciously control. It's a gift from nature, from evolution, from the continuous chain of life reaching back to the first organisms. Every day, your body makes millions of new blood cells, using materials from the food you eat. Your bone marrow works tirelessly, your kidneys regulate carefully, your heart pumps faithfully. All of this happens automatically, supporting you without asking for thanks or recognition. Perhaps it's worth taking a moment to appreciate this gift. Your blood is working right now as you rest, doing the thousands of tasks that keep you alive. It will continue working tonight as you sleep, tomorrow as you wake, throughout your life. It asks only that you care for it reasonably through decent nutrition, sufficient hydration, avoiding excessive harm. In return, blood gives you everything: the energy to move and think, the immune protection to survive in a world of pathogens, the healing capacity to recover from injury, the oxygen needed for consciousness itself. Without blood, you would not exist. With it, you have life. The quiet maintenance. Much of what blood does is simply maintenance. It's not dramatic or exciting, but it's essential. Cell by cell, moment by moment, blood delivers what's needed and removes what's not. This quiet work is what allows everything else to happen. Your thoughts right now are supported by blood delivering glucose and oxygen to your brain. Your muscles maintaining your posture are fueled by blood. Your stomach digesting your last meal relies on blood flow. Your immune system patrolling for threats depends on blood circulation. Even when you're completely still, even when you're asleep, this maintenance continues. Your core temperature is regulated. Your kidneys are filtering. Your liver is processing. All of it depends on blood, on the reliable circulation that never stops. There's no grand purpose to this maintenance, no goal beyond continuation. Blood doesn't flow towards some endpoint. It simply flows, maintaining the conditions that allow life. Its existence for its own sake, the body sustaining itself, because that's what living things do. In a way, this is the deepest meaning of blood. It represents life's persistence, the ongoing process of staying alive. Not life in an abstract sense, but life as a concrete, physical reality. Blood makes the abstract concrete, shows us that life is chemistry and circulation, cells and plasma, oxygen and iron. The invitation to rest. As we near the end of this journey through blood, let yourself sink deeper into rest. You've learned about the rivers within, understood their pathways and purposes. Now let that knowledge fade into the background, leaving only awareness of the gentle rhythm. Feel your breathing, slow and regular. With each breath, oxygen enters your blood, carbon dioxide leaves. The exchange happens automatically, perfectly, without needing your attention. Let it continue in its own rhythm. Feel your heartbeat, steady and reliable. With each beat, blood moves through your body, reaching every cell, sustaining every tissue. This has been happening since before you were born. Will continue as long as you live. Trust it. It knows what to do. Let your muscles relax completely. As they do, blood flow to them decreases, redirecting to other areas. Your body is adjusting for rest, for sleep, for restoration. Allow this process. Don't resist. Just let yourself be carried by the natural rhythms of your body. Your blood is working right now. Will work all night while you sleep. It doesn't need your consciousness, your awareness, your effort. It simply needs you to rest, to allow the natural processes of life to continue unobserved. The darkness and the light blood exists in darkness, flowing through vessels shielded from light. It does its work unseen, unremarked. in the interior spaces of the body. Yet it sustains everything we see and experience in the light. Every bright moment of your life, every sunrise you've watched, every face you've loved, every beauty you've witnessed was possible because blood flowed to your brain, delivering oxygen that allowed you to see, to think, to feel. The light you experience exists because of work done in darkness. This is true metaphorically as well. The unseen support, the background processes, the maintenance that goes unnoticed, all of this makes possible the visible achievements and experiences we value. Blood reminds us that the foundations of life are hidden, working quietly to support everything else. As you drift toward sleep now, toward your own darkness of rest and dreaming, remember that life continues in that darkness. Blood flows, cells work, healing happens, memories consolidate, growth occurs. Sleep is not absence, but a different kind of presence, a quiet activity hidden from consciousness. Trust the darkness. Trust the unseen processes. Trust your blood to continue its ancient work while you rest. Let yourself sink into sleep, knowing that life persists, that the river within flows on. That morning will come and you will wake, renewed. The eternal present blood exists only in the present moment. Each red blood cell lives now, carries oxygen now, moves through vessels now. There's no blood of the past or future, only this moment's flowing, this heartbeat's surge, this breath's exchange. In this, blood is like consciousness itself. You only experience the present moment. Memories and plans exist, but you can only think about them now, can only experience anything now. Blood's eternal present mirrors the eternal present of awareness. Perhaps this is another lesson blood offers, the importance of now, not dwelling on past or worrying about future, but simply existing in this moment, breathing now, heart beating now, blood flowing now, life happening now. As you rest here, you exist in this present moment, this breath, this heartbeat, this quiet darkness. Let the past dissolve, let the future wait. Just be here now, in this moment, in this body, with this blood flowing steadily through you. The present moment is all that's real. Everything else is memory or imagination. Blood reminds us of this truth, flowing only now, never then or when, always and only in the immediate present. Life is not a story with past and future, but an ongoing now, moment after moment, each arising and passing, each unique and gone forever. Rest in this now. This present moment is enough. Your blood flows, your heart beats, you breathe. This is sufficient. This is life. The deep letting go to truly rest, to sleep deeply, requires letting go. Letting go of control, of vigilance, of consciousness itself. It requires trust. Trust that your body will continue functioning, that your blood will keep flowing, that you'll survive the vulnerable time of sleep. For our ancestors, sleep was dangerous. Predators hunted at night. Enemies could attack. Sleep required finding safe shelter and trusting that nothing terrible would happen during those hours of helplessness. Yet they slept anyway, because they had to, because the body demands rest. You're safer now, likely lying in a comfortable bed in a secure home. Yet the deep letting go sleep requires still feels vulnerable. Consciousness is precious. Giving it up, even temporarily, requires trust. But your blood will continue flowing. Your heart will continue beating. Your lungs will continue breathing. The body has its own wisdom, its own maintenance routines that need no oversight. You can let go. You can sleep. You will wake. Let your awareness fade now. Let thoughts slow and drift. Let consciousness dissolve into sleep. your blood will carry on without you, doing its work. In the darkness, sustaining life until morning comes, and you wake, restored and renewed. The circle complete. We began this journey considering blood as both ordinary and miraculous. We've explored its components, its pathways, its functions. We've seen how it connects to every part of the body, how it responds to needs, how it has evolved and continues to change. Blood is the most intimate part of you that you never see. It touches every cell, knows every secret your body holds, carries the information of your life. It's both deeply personal and entirely universal, both uniquely yours and utterly human. The river within flows on. It flowed through your ancestors. It flows through you now. It will flow through generations yet unborn. You are a moment in the river's journey, a temporary vessel for this ancient current. But in this moment, the river is yours. This blood, these cells, this plasma, all of it is working for you, sustaining you, giving you the gift of life. However long or short your time may be, blood will flow through it, making each moment possible. Rest now in that knowledge. Let the river carry you into sleep. Let your heart beat on in its own rhythm. Let your blood flow in its eternal dance. All is well. All is as it should be. The ancient patterns continue, life sustaining itself, moment after moment after moment. The final drifting you're breathing is slower now, deeper. Your heartbeat has found its resting rhythm. Blood flows quietly through relaxed vessels, delivering oxygen, carrying away waste, maintaining the internal environment that allows sleep. Your conscious mind is fading, thoughts becoming scattered and dreamlike. This is natural. This is right. Let it happen. Let consciousness dissolve like mist in morning sun, leaving only the deep processes of life continuing in darkness. Your blood doesn't sleep. It flows on, working through the night. Red cells circling endlessly, white cells patrolling, platelets waiting ready, plasma carrying all. The river never stops. Even in your deepest sleep, it flows, keeping you alive, keeping you warm, keeping you whole. Trust this. Trust the wisdom of billions of years of evolution, the perfection of systems refined across eons. Trust your blood to know what to do. It has kept countless billions of humans alive before you. It will keep you alive tonight. So rest. Rest deeply. Let go completely. Sink into sleep like sinking into warm water, supported and safe. Let the darkness enfold you. Let dreams come or not come. Let sleep take you wherever sleep goes. Your blood will be here when you wake, still flowing, still working, still giving life. The river within is eternal, patient, reliable. It asks nothing. It gives everything. It flows on and on and on. Good night. Rest well. Sleep deeply. Let the river carry you into dreams, into darkness, into the deep restoration of sleep. Morning will come. Light will return. But for now, there's only this: the quiet, darkness, the steady heartbeat, the gentle flow of blood, and the sweet release of sleep. And if you happen to still be awake, you can go ahead and reflect on these wonders when you're ready. But if your eyes are heavy, if your mind is drifting, let yourself go completely now. Close your eyes if they're not already closed. Take one more deep breath and let it out slowly, releasing everything, sinking into sleep, into peace, into the deep rest your body needs and deserves. The river flows on, the heart beats on, life continues in the darkness, and you can rest, knowing all is well, all is as it should be, now and through the night and into the morning that will come. Sleep now, sleep well, sleep deeply. Good night.